This is MGF 1107, Chapter 14, Section 3, Part 2, Apportionment Methods. All right, we've already gone over Hamilton's method. Now, one of the rules we got to look at here is, and this is on page 889, quota rule says an apportionment for every group under consideration should always be either the upper quota or the lower quota. You can't mix them both in the same thing. You got to have upper quota. You got to round everything up, or round everything down. So the next one we go to is Jefferson's method. Now, Jefferson's method only really has two steps, but they're kind of more difficult than the others. It says determine a modified divisor such that when each group's modified quota is rounded down to the nearest integer, the total of the integers is the exact number of items to be apportioned. Okay, so these are modified lower quotas. And so what happens here is this. Okay, let's look at this example problem. And again, this is on page 890. It says, consider the Republic of Germanium from example 3 on page 888. Use Jefferson's method to apportion the 250 legislature seats among the 5 states. All right, so here's the information. Here's your states, A, B, C, D, E. Here's your population of each of these states, and here's your total. All right, and so now if we were to take, and what we want to do is just pick a divisor. So we don't really do what we did with Hamilton's method, where we actually calculate a divisor, we pick one. So what's happened here is if we take and we divide the 250 into the 8,800,000, then we get 35,200 as a standard divisor. That would be doing our normal math. So what we're doing in Jefferson's method is we're going to use this 35,200 as a standard, but we're going to drop it down. So instead of 35,200, we're now going to use 35,000. And so what we're doing is we're going to keep dropping this down until we get our modified quota that will be exactly 250. So if I take 1,003,200, which is the population of state A, and divide by the 35,000, I get 28.66. And so over here on page 891 is this chart. And so what's happened here on this chart is we've taken every one of these populations and divided by 35,000. And this is what we've gotten as a standard quota. If we take these, this is what we'd get if we divided by 35,200, by the standard divisor. But if we divide by 35,000, we now get these numbers here. So let me say it again because I might have confused you. The standard quota was taking the 1,003,200 divided by that standard divisor of 35,200. And so that's what all these numbers represent here. These numbers are being divided by 35,200, 35,200. And so what this is showing us here is the value we would have gotten if we would have divided by the standard divisor, which would have been Hamilton's method. Here are the numbers we're getting by dividing these states' populations by the 35,000. And you can see that they've gone up some. If we round down, we got 28, 35, 142, 23, 21. If we add them together, we get 249. So we're missing one legislator or delegate. So what we do then is we drop this quota down from 35,000 to 34,900. And by dropping it down to 34,900, we now get these values. And again, in Jefferson's method, you're taking the lower quota. So what happens is this goes to 28, this goes to 35, this goes to 143, 23, 21. When we round it together, we get 250, and so we're done. So in Jefferson's method, you figure out your standard divisor, and then you drop it down. And you keep dropping it down until when you divide by it and you modify your lower quota, it adds to your exact number that you need. Next one we come to is Webster's method. Webster's method only has 2 steps too. It says determine a modified divisor D such that when each group's modified quota is rounded to the nearest integer, the total of the integers is the exact number of the items to be apportioned. We refer to these as modified rounded quotas. So let's go back to our problem with germanium. There's our populations again. And so what happens here is we know that if we were to take the 250 seats and divide into the 8,800,000, we'd get 35,200, which is the standard divisor. See, in Webster's method, we're going to round it up a little bit. So instead of using 35,200, we're going to use 35,250, round it up a little bit. And when we divide each one of these by 32,250, we get these numbers here. Now, in Webster's method, we round the numbers just like we do normally in math. This is below 0.5, so it's 28. This is above 0.5, 35, so we round up. Above 0.5, so we round up, 142. Below, so we keep the same. Above, so we round it. If we add all these together, so we get the 250, we're in good shape. So remember Webster's method. Webster's method, 2 steps to it. First of all, you're rounding, you're taking the standard divisor and either rounding up or down, it doesn't matter, or making it less than or greater than. And then when you do your modified quotas, you round them just like we do numbers. If it's 0.5 or greater, you round up. If it's below 0.5, you round down. Last method we have to look at. It's called Adams' method. And Adams' method says determine a modified divisor D such that when each group's modified quota is rounded up to the nearest integer, the total of the integers is the exact number of items to be apportioned. So again, let's go back to our germanium problem. And so with Adams' method, okay, the modified quota for each group needs to be slightly smaller than the standard quota. So what we're going to do is we're going to take that 35,200, which was our standard divisor, and go up. In this case, they go up to 35,400. So again, if we look at this in terms of Adams' method, again, this number here, this standard quota number here is dividing all the population numbers by 35,200. This modified quota is now dividing all the populations by 35,400. And so if you look at what we're doing, we're rounding everything up. So this 28.34 becomes 29, 35, 141, 23, 22. When we add them, we get 250. So in Adams' method, we're going to modify the divisor by raising it higher. And then we're going to round all of our quotas up. We're going to use an upper quota. If you look on page 897, there's a great chart which explains the different methods of voting processes, different voting methods. And then out to the side here, it talks about the apportionment. Okay, so if we look at this, Hamilton's method favors larger states. Jefferson's favors larger states. Whereas Webster's and Adams favor smaller states. So you can see that there's not really an apportionment method that's fair to everything. So you have to really work with the math in order to try to make it as fair as possible.